Hello everyone! Welcome to Miscellaneous Tidbits, the show where we explore different concepts that may or may not connect to different things in calculus, linear algebra, and just general topics. This video is going to be about imaginary numbers. These things are unlike any number we've worked with because they have some neat properties and their existence has crazy implications. Hang on, is this video too long for you? Here are the formulas. Let me know what you did with that extra free time, but just so you know, you're going to miss out on literally the coolest fractal ever created and what is considered the most beautiful equation in all of math. To start off, let's ask the question that likely everybody had when they were learning about square roots. What is the square root of a negative number? To answer this question, let's first answer the question, what is a square root? Plain and simple, it's where you find one number that you can multiply by itself to get the number you started with. So the square root of 4 is 2, since 2 squared is 4. The square root of 4 is also negative 2, since 2 squared is 4, and a negative times a negative equals a positive. So then, does the square root of a negative number have any meaning at all? No, but we can say it does. Let's play my favorite game, Math God. All you have to do is declare something, and that thing comes into existence. Now, here's the thing. We can't do this willy-nilly. What we create must survive logic. So, let's declare the existence of a number that is the square root of negative 1. Bam! It now exists. We'll name our new creation I, after the fact that it is completely imaginary. So now, we must see what logical things we can do with it. First of all, I is a number, so we can ask questions related to the different properties of numbers. For example, where is it on the number line? How does addition, subtraction, multiplication, and division work? How does it behave with other numbers? What does the absolute value mean for I? What does it mean to have I as an exponent? Can it be used in functions? Lots of questions, so buckle up, we're going to take these one by one. First up, basic arithmetic, featuring addition. I plus I is... well, that's weird. What do we call this? I mean, 1 plus 1 is 2 times 1, so maybe I plus I equals 2 times I? But we can simplify 2 times 1 to just 2, so can we do that with I? Now, if we replace I with square root of negative 1, based on square root properties, we can see that no, we actually can't simplify this further. So I plus I equals 2I. Okay, great. I times I is negative 1, since I is defined as the square root of negative 1. I divided by I is 1, since any number divided by itself is 1. See, I is just another number. So what is 2 plus I equal to? Again, if we replaced I with square root of negative 1, we see that, actually, we can't simplify this. So 2 plus I is 2 plus I. It's like 2 plus I is its own number, even though it is the sum of two other numbers. Now mind you, that's nothing unusual. 6 is its own number, even though it is the sum of 2 and 4, but 2 plus I is like if we had no way to write 6 and was instead forced to write 2 plus 4 to mean 6. Which means if you wanted to double the value of 2 plus I, you would have to use the distributive property to get 4 plus 2I. So I can have coefficients like a variable, but it cannot be combined with regular numbers. Okay, for convenience purposes, let's now call a number of the form a plus bi as a quote-unquote complex number, mainly to differentiate it from an imaginary number, which would just be I by itself, or some coefficient of I. But now that we have complex numbers, how do we do division? What does 1 divided by 2 plus I even mean? For that, let's take a look at 2 minus I. We already said that the square root of negative 1 is I, but that also means the square root of negative 1 is also negative I. After all, I squared is -1, and a negative times a negative is a positive. So 2 plus I and 2 minus I share a connection. Let's see what happens when we multiply 1 divided by 2 plus I by a fancy 1 consisting of 2 minus I divided by 2 minus I. We can use FOIL to figure out what 2 plus I times 2 minus I is. And yes, I just FOILed your plan. And we know what I squared is. It's -1. And there's our answer. 1 divided by 2 plus I is 2 minus I divided by 5. Let's give this 2 minus 1 a name. How about conjugate, since it seems to be an alternate form of basically the same thing, just like how verb conjugations are just alternate forms of the same verbs. And since it's still a complex number, 2 plus I and 2 minus I are complex conjugates. And that brings us to the next big question. Where is I on the number line? I seems to behave unlike any number we have seen so far. Here's a fun fact about the number line. You can reach any real number from any other real number by just using addition and scalar multiplication. But the fact that I is only reachable with square roots indicates that I is actually not on the number line, which is why we don't encounter it when we're working with real numbers. One way we can fit I into the number line is to look at the fact that 2 plus I is not reducible further. Which means that in order to fit numbers like I and 2 plus I, one thing we can do is extend the number line to 2 dimensions. This horizontal line is what we're most familiar with, the real numbers. Any number that is a coefficient of I goes on the vertical axis, which we can just call the imaginary axis. With this new model, the number 4 plus 2y is basically the same as describing a point with coordinates 4 and 2. Except now, instead of having to deal with 2 different numbers, we can just deal with one 2-dimensional number. And here we can also see that the complex conjugate is that point reflected across the real axis. And now that we have 2-dimensional numbers, what does the absolute value mean? Remember, the absolute value is defined as the distance between that number and 0. Well, now, this 0 can be written as 0 plus 0i. And actually, this distance idea doesn't change with the fact that now we have 2-dimensional numbers. All that changes is how we calculate it. So, we used to just chop off the positive and negative sign. Now we use the Pythagorean theorem. So let's say we wanted to find the absolute value of 3 plus 4i. 3 plus 4i is located here on the number plane. It's 3 units right and 4 units up from the number 0 plus 0i. So the straight line distance between 0 plus 0i and 3 plus 4i is the square root of 3 squared plus 4 squared, which is 5. Now notice also, this distance can't be negative, which matches what we already know about absolute values. And it can't be imaginary, since triangles only care about this distance, and I is used to describe the position. Now for probably the biggest question of all. What does it mean to have I as an exponent? In order for our imaginary creation to survive this test of logic, we need to look at what exponents actually mean. Exponents are taught as repeated multiplication, just like multiplication is taught as repeated addition. So 2 cubed is 2 times 2 times 2. But if we're trying to find 2 to the I, now the amount of times we're multiplying by 2 is imaginary. And that is an issue that I unfortunately have not found a satisfying way to resolve. Okay, so e is a pretty special number. It's what you get when you take the equation 1 plus 1 over n, all that to the n, and let n approach infinity. E is irrational, just like pi. And there's an ongoing debate on whether pi plus e is rational or not, although it does make a pretty sweet pie. The function e to the x models continuous exponential growth, and it is its own derivative and integral, which is pretty cool. Now where it comes into talking about I is that 2 to the I can be rewritten as e to the natural log of 2 times I. How is that useful? Well, it's just natural to talk about it. So now we have a multiple of I in the exponent of e. What does this mean? Well, one special property of e to the is that rather than repeated multiplication, this actually rotates the unit circle n radians. So 2 to the I, or e to the natural log of 2 times I, rotates along the unit circle natural log of 2 radians. The result is wherever this point lands, with the x and y coordinates written as one complex number. Now, we're using radians, which have the neat property that this curvy distance is the same as the angle. And trig gives us a really neat way to turn angles into coordinates. So in general, e to the ni equals cosine of n plus I times sine of n. If we looked at a specific case where n equals pi, we get what is often considered the most beautiful equation in all of math. E to the I times pi equals -1. And if you wanted to make it cooler, turn it into e to the I times pi plus 1 equals 0. And the reason this is so beautiful is it combines 5 of the most useful numbers in all of math, e, I, pi, 1, and 0, into one simple-looking equation. Now, admittedly, it's a roundabout way of showing it, but I hope it gets the point across. Exponents work as normal, but as soon as you have I in your exponent, you're not repeatedly multiplying, you're rotating around the unit circle in radians. A final logic test. Can I be used in functions? And the answer is yes, yes, 100% yes. Let's take a look at polynomials. There are so-called roots, where the polynomial crosses the x-axis. How many roots one of these functions has depends on x's highest exponent. So if your largest exponent is x to the 7th, that's 7 roots, some of which might be repeated. Now hang on, what about a function like x squared plus 1? Its highest power is x squared, so it has 2 roots, or 2 places where it crosses the x-axis, or maybe even one place that counts twice. But if you graph x squared plus 1, you see this function actually never crosses the x-axis. So it was robbed of its 2 roots. And this is where I is actually really useful. To find roots, you solve for x in x squared plus 1 equals 0. This becomes x squared equals -1, which becomes x equals the square root of -1. Now previously, we were unable to solve for x, but now we can, because we have defined that the square root of -1 is the numbers positive or negative I. So we did it. 2 roots, both imaginary, but hey, they're roots. And in fact, using the quadratic formula, every x squared type polynomial has 2 roots, even though they might be imaginary. So to all of you quadratic formula haters, try solving x squared plus 2x plus 5 with just factoring. See, using the quadratic formula, the clearly superior method to solving these types of equations, we can do this. One really useful trick with these square roots is that you can split the radicals along multiplication. So the square root of -16 can be written as the square root of -1 times the square root of 16, which would get I times 4, or 4i. And there we go. 2 roots, and would you look at that, they're complex conjugates of each other. A cool thing about polynomials is that if you found one complex root, its complex conjugate is also a root, which means that for a function like x cubed plus 1, it has to cross the x-axis for one real root, and then the other 2 can be imaginary. And that's exactly what we see when we graph it. It crosses the x-axis at x equals -1. And lastly, derivatives, limits, and integrals. They work perfectly fine with I, since I is just a number. If you're taking the derivative of 3 minus I all that to the x, that answer will be the natural log of 3 minus I times 3 minus I to the x. When you put I in, or a complex number, into the limit, you start getting awkward questions like, what does it mean to approach I? And because now that we have 2-dimensional numbers, it's meaningless to say approach from above or approach from below. If you want to know what happens, go watch the Secrets of Calculus section titled 3D Shenanigans, because it deals exactly with this issue. Mind you, it deals with it in the context of 2 variable functions, but All you got to do is replace two-variable with two-dimensional, and you're good to go. Now, if you had two-variable functions where you allowed complex numbers, you get a technically four-dimensional input space, which unfortunately I can't draw for you. It just gets weird. Integrals are even weirder because they are already two-dimensional in nature, so putting a two-dimensional number as its bounds tend to get illogical answers. Instead, you usually see complex numbers showing up in the thing you're integrating. Like, for example, the Fourier transform, where I shows up here in the context of you're rotating along a unit circle. I also shows up when talking about the Riemann zeta function, which is a $1 million question involving infinite series with these complex numbers. Go watch the series and sequences section in the Secrets of Calculus to learn more about that. Okay, our creation stood the test of logic. We answered all our big questions, so now time for the cool stuff. First, we can actually ditch trig functions entirely if we really wanted to, because it turns out sine of x can be written as e to the ix minus e to the negative ix, all that over 2I. And cosine of x can be written as e to the ix plus e to the negative ix, all that over 2. The explanation for that comes from power series and the fact that e to the x equals cosine of x plus I times sine of x. But this video is already getting too long, so proof is left as an exercise for the viewer. Alright. You know why you're here. You want to see the cool fractal that I put in the thumbnail. Not only will I show you the cool fractal, I will show you how to make it yourself. Here's the formula you need. Okay, what is this? We have c, which is our variable. C is a constant, which is more fun if it is complex. This is an iterating function, meaning that when you get an answer, you plug that answer back into the function for z, and then continue that process. We start at z equals 0 because that makes things easier. The big question is, does this function value maintain an absolute value less than 2, or does it diverge to infinity? Now this is where a computer comes in, because nobody can test out infinite iterations, and it's not always clear. So here's what you do. Pick a c value and test it out, say 200 iterations. If by the end your complex number's absolute value is less than 2, put a black dot where that original c value was. Now, if after 201 iterations you find that it actually does get bigger than 2, you can use a different color, say orange. Then you can make a gradient of color for how many iterations it took to figure out what was diverging and what wasn't. And as I presume this gradient of color would increase in intensity as it took more and more iterations to figure out what was diverging. Now, when you test out a ton of points through this and you run an algorithm, you get this majestic fractal. This is only really possible if you use complex numbers. Can you imagine trying to keep track of two coordinates through this whole process? Me neither. You can increase the resolution by changing how many iterations you do. You can zoom in to twist your mind into a pretzel. You can print it out as a poster. It's up to you from here. This fractal was first discovered by Benoit B. Mandelbrot. What does the B stand for? Well, it stands for Benoit B. Mandelbrot. Yes, that is an actual joke the guy made about his own name. So there we go. What started as wondering what the square root of -1 was led to two-dimensional numbers consisting of a real and imaginary part. They act just like you would expect numbers to behave, and e to the ni means rotate along the unit circle n radians, which leads to the most beautiful equation in all of math. These numbers let polynomials get back to their roots even when algebra robbed them of that chance. And lastly, the fact that they are two-dimensional numbers lets you make cool fractals when you combine them with function and computer concepts like iteration. I hope you found this helpful, and I'll see you next time.